Okay, now let's take a look at this example problem that we previously solved. Remember that we have a beam member and we have a truss member, an inclined truss member. Now in our previous solution, we assigned 2 degrees of freedoms at point B, translation and rotation. Now the first member will be member AB, the second member was member DB. The local degrees of freedom of member AB was actually matching the structural degrees of freedom, so we didn't have any problem here. But when we have an inclined member like that, its local the directions of its local degrees of freedom were different than the structural degrees of freedom, so we had to do some geometry transformation, manual transformations and so on. Now since we have derived the stiffness matrix of a truss member in global coordinate system, now we will see how we can use it and how we can further simplify the solution of such a problem. So let's first do the discretization, but before doing that, let me define the global directions. So this is global Y, that's global X. So let's put a note, this is our global axis or coordinate, that's right, coordinate system. Now I can do the discretization. I will not draw the cantilever, let's assume that we already handled that. So this is the first member, the beam member. This is the start node, then this will be the end node. Now node B, and I have this inclined truss member. Let's show that it has 2 nodes. Let's first show the structural degrees of freedom. So we have translation, let's call it D1, and rotation. So the structural degrees of freedoms are all defined in with respect to the global coordinate system. So let's name these as structural degrees of freedom. Now let's show the local degrees of freedom for each member. So I'll start from the first member. That's our first member, start node, end node. And the local degrees of freedoms are as follows. But before showing the local degrees of freedom, let's first show the local axis. So that will be the x prime axis. That's the y prime axis. Remember that we were using the local axis in also differential equation solution to simplify our solution. So we start using it again, showing it again. So that's local x, that's local y. So let me also show the global directions. Again, this is x, this is y. Now for the second member, I will choose it this way. And my local axis for the second member will be as follows. That will be x prime, and that will be y prime for the second member. Okay, now let's show the rotation angle. Now for the first one, remember that for the rotation angle we will be looking at the angles between the global x and the local x. So they are parallel. So for the first one, actually we don't have to do any transformation. Theta is equal to 0. The critical point here is the second member, of course. So let's first show the global x, and the rotation angle, you start from global x, go to the local x in the counterclockwise direction. So that will be the rotation angle theta for the second member. Now let's show the local degrees of freedoms. The first member, start node, this is 1, 2, 3, and 4. that's a beam member. We already have the local stiffness matrix, and since theta is equal to 0, the local stiffness and the global stiffness is exactly the same. Now the second member is a truss member, so I have only axial deformation on this one. Now that's the rotation angle. Now I'm showing all the degrees of freedoms in the global direction because I will be using the global stiffness matrix. So that will be D1, D2. Remember that I'm showing all the degrees of freedom in global directions. D4. I forgot to write D here, so let me put the D's here also. Okay. Now remember that the first degrees of freedom at the start node will be in the global x direction. The second degrees of freedom at the start node will be in the global y's. The third degrees of freedom will be at the end node, it's in the global x direction. And the fourth degrees of freedom will be again at the end node in the global y direction. So we determine everything. So we are showing in the discretization all the global degrees of freedom, local degrees of freedom, members, nodes, and all the rotation angles. Now we can actually assemble the stiffness matrix. I'm not working on the force matrix here. There's no difference in that. So the force matrix will be the same. So let's take a look at the stiffness matrix. Case 1. So we have a unit translation, but no rotation. So in order to create a unit translation, I need a force that's equal to K11. So in order to create a unit translation in the D1 direction, the contribution or the resistance coming from the first member will be K33. So let's write this down. K33 coming from the first member plus the contribution coming from the second member. Again, let's take a look at here, D1, and the stiffness coefficient that matches D1 direction is D4. So that resistance will be K44 coming from the second member. Of course, here K44 will be obtained from the global stiffness matrix. So K33 is 12 EI over 4 cubed. Now K44, so I will be using this stiffness matrix. Remember that now these are my degrees of freedoms. So in order to create a unit translation in the 4 direction, I will be needing EA over L multiplied by sine square theta. So let's write it down. So this is EA over 5 multiplied by sine square theta, theta being the rotation angle. So when you evaluate that, that's equal to 0.2595 EI. Now the second, the off diagonal for the first case is K21. That's equal to, let's again take a look at this figure. So I'm give a unit direction. I want to keep the rotation equal to 0. There's no contribution coming from the second member. The only contribution will come from the first member, and that will be equal to K43 prime, which is equal to 0.375 EI. Now K22 is rotation, so we don't have the contribution of the truss member, and what we get is from this resistance is coming from the first member, and that will be equal to K44. K44 coming from the first member, and that's equal to EI. So as you see, we obtain the same stiffness matrix. The only difference is I didn't deal with the giving a unit translation in the vertical direction to this force truss member, and try to calculate how much axial force do I have on this one. So I did it once in this case, and I just directly used it. Now let's say that we did the solution. We have the stiffness matrix, we know the force vector, and once we obtain the solution, d1 will be equal to minus 536.3 divided by EI, and d2 will be equal to minus 211.1 divided by EI. So these are the displacements. Now let's see how we can recover the member end forces. I will do it for the truss member. There is nothing special for the beam member. We already worked on it. Now let me draw the truss members, its local and global degrees of freedoms. So this is our truss member, and the degrees of freedoms for this truss member is as follows in the local directions. That's d1, that's d2, that's d3, and that's d4. Okay, now the ones in the global direction is as follows. Let's repeat how we determine that. D1 will be at the start node in the global direction. D2 will be at the end node, start node in the global y direction. D3 end node global x. D4 end node global y. Okay, so these are the global, and these ones are the local. So what do we know about the displacements of this member? We know that point B translates in the upward direction by this amount. So it means for this member, for the truss member, we know that d4 in the global direction is equal to minus 536.3 divided by EI. So let's write it down. So U in the global directions is equal to d1 global is equal to 0, d2 global 0, d3 global is 0, minus 536.3 divided by EI. So that's the displacements in global direction. So what about how can I obtain the displacements in local directions? Because if I know what D1 and D3 is, I can directly calculate what the axial force on this truss member is. So we know that U prime, displacements in local coordinate system, is equal to rotation matrix multiplied by the displacements, member end displacements in global coordinate system. So as you see, this is for us global to local transformation. So in that case, U prime will be equal to, let's write the rotation matrix. So we know here what the rotation matrix is. 0.8 cosine theta, 0.6 minus 0.6, 0.8, and I'll have the same coefficients here, and the rest is 0. Oops, that's right. Multiplied by the global displacements 0, 0, 0 minus 536.3 divided by EI. And when you do that calculation, let's not write EI, but let's write, this is EA, the same, they have the same magnitude, so let's write everything in terms of EA. And when you evaluate that, we obtain displacements in local directions are as follows: 0, 0, minus 321.78 divided by EA, minus 429.04 divided by EA. So these are the displacements in the local directions. So what I know is, in the 3 direction, the translation is 321, and in the D4 direction, it's 429. So if I want to calculate the thrust force, the total compression or the shortening of this member, since D1 is equal to 0, is equal to the value of D3. So the shortening is minus 321.78 divided by EA, multiplied by the stiffness of axial stiffness of the truss, which is EA over L or EA over 5. So the thrust force can be obtained as equal to minus 64.36 kilonewtons. So that's the axial force on the truss. Okay, so that's another way of obtaining the membrane forces. You can of course always determine what D3 and D4 is by using the geometry or the trigonometry, but instead we just use our derivation, and this type of transformation will always work. There's another alternative way which we don't use much, but let me just very briefly discuss it. Now here what I did is I first transformed the membrane displacements, but the other option is, if you want to use, is as follows. The membrane forces in global direction is, you multiply the global stiffness matrix, this one, with the global membrane displacements, which is that one, and you obtain the forces in the global directions, and then again you perform the transformation. F prime again is equal to rotation matrix multiplied by F. It's another global to local transformation, and this will give you the same result. Is it practical? No, I think this approach is more practical, but this is the mathematically equivalent. So this will give you the same result.